Hello, everyone. So we saw that whenever there's a change in the price of an input, uh, the firm is likely going to change its input mix in such a way that it uses more of the cheaper input. So using this idea from the perspective of cost functions, we're going to revisit this notion of substitutability among inputs. So in the production function chapter, we saw that there is a measure which indicates how substitutable inputs are in a production function. So if there is infinite degree of substitutability, then you can just swap k in place of L or L in place of k and get the job done. If substitutability is very limited, if it is almost zero, then you need inputs in fixed proportions to get the job done. So we came up with a particular measure of this called the elasticity of substitution, denoted using the letter sigma. Sigma is nothing but the percentage change in k by L for a percentage change in the rate of technical substitution. Now, from the cost functions chapter, we are actually going to come up with another measure of elasticity of substitution, which is actually easier to capture in practice. Now, recall that when we are minimizing costs, at that point of tangency between the budget line and the isoquant, their slopes are equal. So the rate of technical substitution actually equals W by V at the point of optimality. So if we were to do this substitution into our expression for sigma, our elasticity of substitution takes on a different flavor. And we now write down something called S, which is actually percentage change in k by L divided by percentage change in the price ratio of inputs. So in place of RTS, all I've done is substituted with the change in the W over V ratio. So the point to note here is that when your sigma applies to, you can compute the elasticity at any point on your isoquant, but this version of your elasticity coming from S, that applies only to the optimal point where you're minimizing costs, okay? Because that's where we're substituting for RTS with W by V. And so you have to keep that in mind. But the biggest advantage here is that this is a lot easier to calculate because we know K by L ratio, we can get that from the data. We can also get W by V information from our data. We can capture wages and we can capture price of capital. So this information is available to us a lot easier. The only caveat is that you can compute this only at that cost minimization optimum. And like sigma, S is also non-negative. So whenever there's a change in the price ratio, that's also going to bring forth positive changes in the K by L ratio. So if W by V increases, then it means labor becomes more expensive. Then you're going to switch towards capital, which is the cheaper input. So your K by L will also increase. So S is also non-negative. A larger value of S will tell you that for any change in the price of these inputs, you're going to see a larger change in the input mix. So for even a small change in the price of these inputs, you're seeing a huge level of substitutability. You're seeing a huge change in the input mix, which indicates a high level of substitutability. Converse, if for a given change in the price, if the change in input mix is not substantial, then it means there's a lesser degree of substitutability there. Now, we could expand this to the n inputs case and compute the degree of elasticity of substitution between any two inputs, xi and xj. So, sorry, there's a typo there. We should say xi and xj. So we can write the formula in a similar way as it was in the two input case. Now, the important aspect of how this differs from the previous version of elasticity of substitution that we learned in the earlier chapter is that here, when you're talking of substitutability between two inputs, we tend to keep the other inputs fixed. Now, that's not a very realistic scenario, right? So it's not a very realistic scenario to imagine that you're changing, when one input becomes more expensive, you're only changing one of those uh, inputs and substituting that with a cheaper input, but not doing anything else to the other inputs. So that was a problematic assumption when we learned about this elasticity formula in the previous chapter. But now, once you start looking at it in this current version, as you're seeing on the slides right now, where you're looking at a change in the ratio of inputs to the change in the ratio of their prices, we have the flexibility to adjust the other inputs also. And these elasticities are actually called Morishima elasticities, named after an economist who came up with this idea. So, example, if the capital energy ratio, let's say that changes in response to a change in their relative prices, when your capital and energy prices are changing, we're also going to be changing how much labor we're using. So it's not like we'll keep labor constant and only focus on these two inputs. So this version of this elasticity formula allows for such changes also. And naturally, it is a more realistic scenario. So with that, I think I'll bring this video to a close. And in the next video, we'll speak about how technical change can show up in cost functions. So I'll see you there.